Good morning, everyone. This is Julia Gerlach, Associate Editor for Precision Farming Dealer, and welcome to the next episode in our Precision Farming Dealer webinar series. Today's event is brought to you and other pre-registrants free, courtesy of OptiSurface. 80% of crop yield loss within a field over time can often be attributed to variable moisture availability, both too little and too much. Excess moisture also plays havoc with machinery operations and farm efficiency. By improving surface topography, optimum surface landforming has shown to provide a range of profit-boosting benefits at a relatively low cost per acre, resulting in a high return on investment, or ROI. After an excessively wet spring in many parts of the U.S., improving drainage and irrigation by optimizing field topography at a relatively low cost may be an option for farm customers in the future. In today's webinar event, Graeme Cox, Engineering Director for Davco Farming, will discuss the bottom line benefits of precision optimum surface landforming and how the system can dramatically improve surface drainage and water infiltration for farm customers. And before we begin, just a couple of quick housekeeping items. On your screen, there is an arrow you can click on that will open up a question field and allow you to submit questions at any time during the presentation. Time permitting, we'll look to answer as many of those submissions as possible following the presentation. If for any reason your internet connection, or even our connection should happen to fail at some point, and it looks like the webinar has been interrupted, just go back to that email you received earlier telling you how to join the webinar, and you can re-enter the webinar that way. With that said, we are ready to roll. Thanks again for joining us, and we're going to now turn over the controls to Graeme Cox to begin his webinar presentation. Hey there, Graeme.
Thanks, Julia. Thanks for the introduction, and I'm excited to be here and explain some of the insights that we've learned over the last 10 years with this technology. Just a quick background on me. I'm an agricultural engineer, and I have a PhD in precision farming. Spent many years working with farm irrigation and water management, and also assisting the operation of a sugarcane farming operation in Australia, one of the largest private farms. And for that farming operation, we had a particular problem we wanted to solve, and we solved it. We had to develop it ourselves with OptiSurface, and that's what we're going to discuss today. I'm sitting in a hotel in Chicago at the moment. We've just halfway through a road trip through the US and Canada. We started in Mississippi and went through Arkansas, Missouri, Illinois, Indiana, and Iowa, and then we've just come back to Illinois. It's been a great trip, but it's also been a good year to highlight or see the issues that excess water can do to crop production. And we've met with many existing clients and potential clients who are looking for better options to handle the what appears to be increasingly wet springs and growing seasons. So today we'll cover a few things. Firstly, why water is king when it comes to farm profits and production, and a new GPS-based solution available to manage water better. And we'll tackle some case studies that show the return on investment that can be gained. So first thing is, this is my 80-20 rule of precision agriculture. If you haven't heard of the 80-20 rule, it's 80% of the gains or impact in areas is typically due to one factor, or 20% of the causes. In this case, 80% of the yield variability and loss is typically caused by one thing, and that's water. This graph here shows an example of this for Iowa corn, measured between over the last 60 years or so. And you can see drought and excess moisture and flooding cover most of the losses, and this would have been determined over state level, not field based. So in this webinar, we're going to be looking particularly at the excess moisture side of things and how we can better manage that side of it. The technology we're going to discuss also helps with drought in terms of improving irrigation and infiltration uniformity, but the main benefit we're going to discuss here is the excess moisture. So yield maps support this 80-20 rule. If you look at most yield maps, you'll see that 80% of yield variability is caused by moisture. Often it's water standing in the field, drowning the crop, and other times it can be drought related or insufficient moisture due to sandy soils or runoff from areas. While we were traveling through Missouri, we met a client or prospective client down there, and he gave a good analogy about water versus nutrients. He was struggling to explain to his agronomist in the company why water is the most important thing to manage in his operation. And he told us this analogy that if you're thrown overboard into the ocean and you're abandoned, what are you gonna starve first in terms of lack of nutrients, or are you going to drown first? And it's pretty obvious that drowning is a higher risk, and that's the same problem that our crops have. They can start drowning within 24 hours of being in ponded water, whereas nutrients will take a lot longer to impact. Same with you. So as well as drowning the crop, the plant, there's many other impacts that excess water has on farming operation. In this example, we can see the nitrogen loss in this crop due to the depressions, volatilizing water or leaching nitrogen out of the system. Sorry, volatilizing nitrogen or leaching it below the root zone. And we also know that it can have a huge impact on machinery operations. You could have 90% of the field ready to commence planting or spraying or harvesting, and there's 10% that isn't ready, and that can hold up operations. And just when that wet area dries out, you get another rainfall event, and those wet areas fill up with water again. And in this case, this spray operator wasn't content with waiting around for that area to dry out again, so he tried to get in there and plant. Get in there and spray, and you can see that that wasn't a good decision. But the 90% of the field around him needed weed control or nutrients, whatever he was applying, and that part of the field, even though it's not being drowned, it's losing yield because it's not getting the machinery operations treatments that are required so it can fulfill its potential as well. This is an example to show the impact of water standing on yield, and there's plenty of information around on this, but this is a particularly clear image that I found when I was driving on the road, and you can see that as the water, this is in a furrowed situation, which is different to most of the cropping around here, but the principle still holds true. The deeper the water beside the crop, the lower the crop production. And then as you get as the water gets shallower, you can see that crop gets healthier and higher yielding. So only 2 inches of water ponding can mean 0 yield. And that 2 inches is more common than you think. It can be even caused by traffic, machinery traffic, creating mini ridges. Here's another example from the morningfarmreport.com, where they showed the yield, harvest being delayed on this part of the field, and probably maybe abandoned as well. So this is what typically happens. They'll be driving along and they'll hit the edge of the wet spot, and then they'll stop harvesting this area. They'll waste extra time turning around to go around this area to start again. And then if they get completely stuck, they can damage machinery, pulling it out, greatly adding to the time and expense of harvesting or any machinery operation for that matter. So that's why we say focus on fixing the water problems first, as it often has the highest return on investment. So what are the drainage options that you can undertake to improve these problems? Firstly, you can ridge or furrow or create beds in your field and plant the crop on top of it. It's not commonly done. Or you can put in subsurface tile, which is commonly done around here. I fully understand the situation. You can also cut ditches and drain through the field. You can land plane, which is just dragging a blade behind a tractor, typically a long wheelbase, to smooth out the field surface. You can carry out laser leveling or laser grading, which is a technology that's been around for 70 years and was actually developed in the Midwest here, but typically isn't applicable for any of the dryland, the unirrigated farming areas around the Corn Belt, because the excess soil is required to move. And then the new opportunity that's come along is what we call optimum surface landforming. We'll go into that. Before we do that, this shows you, we'll go through the limitation of those different techniques. In this case, we're looking at the limitations of ridges and furrows and beds. You can take a field that drains reasonably well and put ridges and furrows in it, and then create drainage problems like this field here. Because the water would normally, in this case, flow in this direction to get off the field. As soon as you put up ridges or furrows, that water can no longer flow out there. So then you've created these mini dams, and then trafficking through here with machinery is obviously going to exacerbate that problem. And then you can, so you can take a field that is working okay without ridges and make it worse. Now I'm not saying that ridges and furrows are bad. We farm 7,000 acres of sugarcane on furrows, mainly for furrow irrigation, but even some areas that we are drip irrigating, we also grow on beds because of the micro drainage benefits that furrows allow in the area. But to put those beds in, we still carry out landforming, and that's why we developed this tool actually, is because we wanted to drain these fields with lower earthworks and laser technology. This photo shows the limitations of tile. So this field here was actually tiled. This was after a significant rainfall event. And most people think that tile will solve their drainage problems, but if tile's only designed to take away, say, 3/8 of an inch of water, if you have a depression that is, say, 4 inches deep in your field, and it takes 8 days for that water to drain away, then you could have lost all or most of your yield in that area. So tile, some contractors oversize tile to try and compensate for this, but only by a small amount. Surface inlets into tile is a common occurrence, but surface inlets are a pain to maintain and farm around. So we believe that landforming complements tile, and we'll discuss that later. So the other option is ditching through a field or putting drains through. This is probably the worst case I've seen of ditches, and I'm not saying every field's like this, but as soon as you put a ditch into a field, even if it's a shallow drain, you have to maintain that drain. And if it starts to get too deep, you have to start farming around it. In this case here, the drains, this pivot were actually 6 foot deep. This is the survey of that field. The drains haven't been tied together quite in lines, but yeah, the very, very deep drains. So that means they had to farm each of these little areas. They had to drive around and farm them separately. We've just come from a client in the lower southern part of Illinois, and he had 5 ditches through a field, and he basically landformed that field, removed all those ditches, and they used to be farmed as 5 separate blocks. Now he's farming as one single block. So greatly improving his machinery efficiency and operation, and also solving the water ponding problems that were existent in that field as well, that the drains weren't solving. So we've covered those first 3. The next 3, land planing. The problem with land planing is that it can be useful in smoothing out a field surface and improving drainage, but what can often happen is you will take a depression that might be 4 inches deep, and with a land plane you'll spread that out. Instead of having a quarter of a hectare with 4 inches deep, it might be a quarter of an acre, 4 inches deep. You might end up with depression that's 1 acre, 1 inch deep. So you've actually probably cost you more in yield loss because you're impacting 4 acres instead of 1 now. Laser leveling land grading, I mentioned before, is typically not applicable in this part of the world because of the earthworks are just far too excessive. I think we'll talk about compare land grading to laser leveling to optimum surface landforming in a second. So what is optimum surface landforming? Basically it's the process of shaping the land surface to optimize 3D surfaces using earth moving equipment controlled by RTK GPS machine control. This is actually our machine in Australia, and you can see this GPS receiver on the earth moving scraper, and that's as opposed to a laser receiver that you traditionally see on these machines. So what are we OptiSurface landform? Well, it's to solve all the problems that we've mentioned previously. So we achieve all the drainage benefits by eliminating all the reverse grades that form depressions in the field. We also smooth out the surface to promote more uniform infiltration. And the advantages over traditional laser grading is that we have much lower earthworks, typically 80% lower, 80% lower, and also much lower topsoil movement goes along with that. This is actually our design on the right hand side here. You can see it's a curved surface, and you can only achieve that design in the field using 3D GPS control system. You can't use a laser control system to create this this land surface. Another way to explain the difference between laser and landforming is this is a laser simulated laser grade through a field topography. We've exaggerated the elevation scale on the left, but see the laser is cutting straight through a straight line. In this case, in this field, it was a planar best fit through the field, so we're just looking at one cross section through the field. The downslope of that plane was 0.12%, quite small. The naked eye can barely pick that up. In fact, the naked eye can generally only pick up slopes of 1% or more, so definitely can pick that up. The field earthworks for a laser plane like this through the field was 750 cubic meters per hectare, which is about half that for cubic yards per acre, so it's about 350, 375 cubic yards per acre. Now this is a long section for an OptiSurface field. You can see it's following the natural topography. In this case up here, it's had to fill in that depression to get it to drain from the minimum slope. And then once it comes down off that area, it's had to cut that area again to get this area drained. But once it's come down and now it's using the natural slope. If you've done variable grade tile design, you'll understand it's a similar concept, except we're applying it across the surface. And it's a bit more complex than tile design because we're optimizing the design across the surface, not one run at a time. So in this case, the downslope ranged from 0.05% to 0.7%, and the earthworks dropped down to 116 cubic meters per hectare, or by 8%. So all the benefits of high yield, high quality, and the higher profit that you get with improved water management. I won't go into that. Kind of covered all those problems that we're solving. But there are some other ones, I guess. Reduced weed problems. Weeds grow better often grow better in these drowned out areas. They'll also diseases can proliferate in wetter areas as well, in the soil and help spread it through the air. Many other issues, many other benefits to this, including your water management. Okay, so here we've got a number of different surface types that we can apply to a field, and they suit different situations or farming size. Uh, the OptiSurface one way is basically drains along furrows in one direction. So this is an example of it here. There's positive down slope continuously in this direction here. So if you had furrow irrigation, you could put water at the top end here, furrow down, the water run down the furrow and get to the end. That can be also used in dry land, unirrigated situations where you have furrows or beds for some reason. Could be growing vegetables or any crop, and you'll get drainage down there, down the furrow as well. In this case here, the next example is a two-way furrow, and what we call it two-way because it can fall down a furrow, but two ways off a ridge. So in this case, the water is running this direction, and actually this was a field that was well, this is a lateral move field, lateral move irrigator, and the problem they were having is the wheel tracks of the lateral move, which were running this way, were basically stopping water running where it wanted to naturally drain is this way. So what we did here was create this series of, and it was very flat in this direction. So we created these ridges, valleys, we call them. So ridge, valley, ridge, valley, ridge. So in terms of the pivot, the lateral move irrigator, linear move irrigator, the water would travel down the wheel track to the valley, and then they would add some cross drains here with often they can just drive a machine along these low spots, and that would give it enough of a drain for that water to exit. But you can see there's down slope to that point, and then each of these cross drains will take the water out to this edge. The four-way example is more applicable for situations in the Midwest where we're growing crops, in furrows or beds, and we just want to remove depressions that are drowning our crop. So we just want continuous slope to the edge of the field, and this is an example of that. So the water would meander its way off the field, look up the edge of the field. We call it four-way because at any point in the field, the water can actually move in four directions. And we have another type that isn't used that often, but we do have some clients who want to farm their centre pivots in a circle because they are growing crops on beds, and they want the centre pivot wheel tracks to follow the beds or the furrows. So in this case here, this centre pivot actually drains in a circular direction. So there's always continuous slope from this high area here around to this drains here. Okay, the next thing I want to discuss was the potential area of application of this technology. Traditionally, laser grading has been used in the surface irrigation market. However, with the development of this GPS landforming, we can now apply it to much larger areas. I think drainage on overhead irrigation, drip irrigation is a big market, and but unirrigated farming is the biggest potential market in terms of acres around the world, and that's what we've seen. Over 50% of the application of this technology is currently in unirrigated farming applications. Okay, now I'd like to move on to case studies, and this is a case study. Actually, it's in Australia, but this farmer was losing half of his crop to ponding in wet years. And this screenshot shows you a field in the background that this is his first field he did. He OptiSurfaced that field, and then this field to the towards the camera was. He said it was like this all over. Had these shallow depressions that were just drowning the crop out, and then in between you'd have some crop. This is the yield map for that field, and he was looking. That photo is looking from the south here, and the red areas are low yielding, and the grey areas actually are no production at all. There's no yield in there. So in this particular field, this is a relatively dry area. They were growing beans. He lost $600 an acre. Sorry, $600 a hectare on average for that year, which is about $200 US per acre. So $70,000. And this is the existing topography of that field. You can see there's about 3 feet fall in 3,600, so it's a very low sloping field. This is where the water would stand in the field when he farmed north-south the assumption here when he farmed north-south is there minor furrows left by planting and spray machinery actually limit water flow perpendicular to that traffic. So he's farming north-south, but generally this field is actually sloping in this direction. So the first thing you should do is switch around to farming east-west, and also and then landforming will solve most of the problems, or the other half of the problems that he's got. So if we look at the comparison with the yield map and the depression map, it's almost a mirror image. So he was very excited to design this field, and or get a design for this field, and that is the design. It's actually a two-way design, because some of this water wanted to flow back this way, and let that flow back this way. This most of it flowed this way, with a minimum slope of 0.05% and maximum slope of 0.5%, and smoothing it factor of 250 meters per percent, which is just a smoothing factor that we apply to get a smooth surface. This is what we call a cut fill map, so it shows you where the soil has to cut from in the yellow, orange, and red areas that we cut, and then where the soil has to be filled in the light blue to purple areas. The green areas basically don't have to be touched too much, but we generally run the blade over it, but there's not much soil movement there. So the average cut in this field is very small. It's only 96 cubic meters per hectare, which is about 50 cubic yards per acre. The average cut was only 70 millimeters, so about 2/3 of an inch. The field is similar. And the earthworks cost is estimated at $250 per hectare. That's only about $100 per acre. And so field cost of $30,000 per year earthworks. So if we look at the return on investment for that field, we've got a cost of $30,000, and in 1 year, that one wet year, we've got a benefit of $70,000. So in a wet year, he's got a 233% return on investment. Now, He only has to do this operation once. Remember, he's not doing this every year. He does it once. He may come back in 5 years and rebrush it, we call it. But this is a one-time operation, and he's been getting the benefits forever. So just on a yield improvement basis, there's over 233% return on investment for that year. On average, it may be lower. Dry years, you're not going to see that benefit, but typically you can pay off this investment in 1 year, in a wet year, what we see in the fields we've designed and analysed. This also ignores any of the benefits that we get from improved machinery, timeliness, reduction in nitrogen loss, reduction in weeds, etc. So you can, in this guy's case, probably increase that benefit, or at least on the average, in terms of the average year, increase the benefit to 200%. Okay, I'm just going to flick to some other case studies in on our website. There's plenty of case studies on the examples. This is a field in Illinois that has, it's a quarter section, and it has about 7 feet of variable of elevation change across it. Again, quite flat, but don't think that this only applies to flat fields. The benefits are more obvious in flat fields because of that's when the opportunity for ponding is more common. But this, we have applied OptiSurface to areas that are more rolling, and combined with drains, shallow drains, and OptiSurface in between, you can get significant benefits on more undulating fields. Okay, so this is the ponding map for this field. You can see there's lots of depressions over it. This was the design surface. It comes out of the design software, and basically that, you see these contours are always falling to the edge of the field. There's no depressions left within the field. This is the gut field map. So in this case, we were in these deep red areas. The cut was about 4 inches, and the purple areas were about 4 inches. So quite small cuts and fills. If you're concerned about topsoil in these areas, which is a common comment we get, you can strip the topsoil off these areas, do the earthworks underneath the subsoil, and then put the topsoil back. It does make the operation a lot more expensive, but for small areas where it's required here, it can be beneficial. This is actually a video of that field. Well, the field is actually this darker one here that's been finished. You can see the neighbours' fields have got water standing all over them, and then this field is completely drained and ready for working. So yeah, there's quite a few pivots around through the Corn Belt, and we have used OptiSurface is used quite a bit in pivots, because a lot of people put pivots in and think they don't have to fix the drainage up. But once you start applying more water with a pivot and rainfall events, etc., you'll end up with worse problems than if you were farming it dryland. This is the existing topography, and the ponding map you can see here shows where it'll hold water. This client was also concerned with runoff from larger areas, from steeper areas of the field that were congregating in those depressions. So we wanted to smooth the surface out as well. This is our design. So you can see that that's the existing topography, and then this is the optimized landform design on top of that. So you can see it's smoothing the surface out and providing positive slope to the whole field. This is the cut fill map, and in this case he was cutting up to a foot in these dark areas, darker red areas, and filling up to a foot in these areas here. In this case, the earthworks were up a bit higher, up towards 177 cubic yards per acre. But the client was extremely happy. His comments were there was no more ponding, dampening off, salt accumulation, water goes on, it goes in as evenly as it goes on. It's a completely different field to work and farm. So we're running out of time, so I'll finish up here. So just to finish a bit more off on the cost-benefit analysis of this, 1 year payback is common, and compared to tile, where 7-year payback is typical, and that's thought is a good investment. I think landforming is very favourable in that regard. In terms of the cost-benefit factor, I won't go into this too much, but the biggest benefit is where you have higher value crop, and where you have a higher loss of yield, and that's where the proportion of the field is affected, the percent of the field affected, and how frequent you have wet years. And there's the cost of doing the job. There's some factors in that. I won't go into those either too much. So in finishing, basically water is king when it comes to yield variability and therefore farm profit. So you should try and fix that first before trying to do any variable rate application, which most precision ag agronomists and people are focusing on. We believe OptiSurface landforming can help in this area in a lot of cases, and a high return on investment is often achieved. I think that's it. Thank you. Thanks for attending, and I'll hand back to Julia to fire up any questions or any thoughts.
Okay, great. Well, thank you so much, Graeme. That was really interesting. And I have to tell you, thinking back to one of your early slides, the one about the 80% of the yield issues being a result of water, that was very eye-opening to me. I really had not ever realized that. And of course, you're right. But that was very illuminating. And I do have a couple of questions. So there was, just early on, you had talked about the mung bean yield losses. And I was wondering, how long does the water have to stand in order to cause those losses that you talked about?
Yeah, not long. Typically, for crops, they can stand in water for 24 hours without any impact to production. But for every 24 hours after that, they can lose 5 to 10% of the yield.
Oh,
So if it's if that water's sitting there for 10 days, then you could have lost half your yield or maybe even all your yield in that area.
wow. Well, and then also, so you may have, I kind of ducked out for a minute, but, and you may have covered this already, but how often does the landforming need to be done in your experience?
Yeah, it's basically the first operation is the most uh, expansive operation. That's where you're shifting most of the soil. And then every 5 years, you may want to come back and just rebrush it, and the cost for that is a lot lower than the initial investment. Yeah.
Okay, okay. Okay, so I do have a question from a listener, and I also want to just encourage other listeners, if you have any questions right now, please type them in and we can get them answered for you. The question that we have from our listener, this goes back to when you were talking about how the landforming works, and you were showing some slides of some sort of sloping land. And the question that came in was, is all the field farmable? So was that an image of, or were those images of fields that were actually farmable fields?
Okay, I'm not sure which images we're talking about, but we're generally working on fields that are all farmable,
Yeah, okay.
and we're just fixing up the problem areas within those fields that may get friendly.
Okay, great. We have another question that has come in. Is there a maximum field size or data point density that we can generate a design for? And that's a question.
We like to keep the data points down to, say, 30,000 points per field, but we have had cases where we've had clients actually use, hundreds of thousands of points for a field is still workable, but it can get a bit heavy to pass that data around and analyze it. But hundreds of thousands of points.
Okay, great. All right, well, unless there are any other questions that are coming in, I think that we have just about wrapped things up. This was a really interesting presentation. Thank you so much, Graeme. I hope you enjoy the rest of your time here in the United States and your trip. And just a reminder to everybody that today's presentation and audio will be made available on the Precision Farming Dealer website. And so on behalf of Graeme Cox and the team at OptiSurface, thanks for joining us today for the webinar.
Thanks, Julia. It's been great.